So today we're going to discuss Zener diode as a voltage regulator. So far we have studied ordinary rectifier diode and also discussed a little bit of Zener diode. So the main difference from ordinary rectifier diode and Zener diode is we usually attach a Zener diode in the circuit in reverse bias, and then in reverse bias it will start conducting after a certain voltage applied to the diode, that is called the Zener breakdown voltage. So just for brief recap, so let me discuss a bit. So this is the symbol of a ordinary diode. This is the symbol of a Zener diode, just for identification purpose. Now if I look the IV characteristic of a ordinary diode, so it will start conducting after some voltage which is very relatively low, which is of the order of 0.7 volt for silicon and around 0.2 volt for germanium when it is in forward bias, and in reverse bias it will almost never conduct, or the current is very low of the order of we can say 0.01 microampere. And the ordinary rectifier diode is designed in such a way that in reverse bias at very high voltage it eventually break down and destroy the diode, whereas in case of Zener diode we discussed that in forward bias Zener diode exactly behaves like a rectifier diode, and if they are made out of silicon, so the knee voltage will be around 0.7 volt, whereas in reverse bias when they are connected in reverse bias at relatively low voltage they can break down, and during the fabrication of diode the doping, the depletion zone concentration etc is varied in such a way that we can control this breakdown voltage Vz, and Vz can be like 6 volt, 3.3 volt, 12 volt, 24 volt, like that. So we have varieties of Zener diode available, and then after breakdown it will act, its resistance almost vanishes and it will show similar characteristic like a diode in forward bias. Now we already discussed there are two types of Zener diode. Actually there are avalanche type of Zener diode and there are also Zener type Zener diode, but anyhow anyway we called all of them as Zener diode. Whatever the case, the main application of this Zener diode we used in a circuit as a voltage regulator, and also it is used in a protective electronics also. If there is a voltage surge and all, so Zener diode can give us a protection. So first discuss, or there is only thing we have in our syllabus is Zener as a voltage regulator. So let me draw a very simple circuit where we can act or apply Zener as a voltage regulator. So this is a battery of varying voltage. So this part, this varying voltage, we are already aware of with this type of thing. So these entire things actually we can think bridge rectifier, attach a bridge rectifier and some filter attached with it, and we actually using some transformer to reduce our main line to some 10 volt, 20 volt, and then we rectify it using rectifier diode, and we are using that voltage source. As we know our main line is not that stable, then and the output voltage VL also has some fluctuation, but if our load need some stable voltage, then the direct use of this DC which is coming from mains, which is actually coming from mains after rectification, is not useful or sometimes cause problem to certain appliance. So as a result, we need to regulate the voltage. So in the circuit, there will be some RS. Circuit is really simple. So this side is the positive side of the battery, this side is the negative side of the battery. As remember, we earlier told that we need to attach the Zener diode in reverse bias. So we're going to attach the Zener diode in reverse bias. So just go a little bit up. So for recap, so this is the inside of the battery, inside of the diode. This is the P side of the diode. Similar thing here also. So look, here we connected the inside with the positive terminal of the battery. That's indicating the diode is in reverse bias. So and this Zener diode has in some breakdown voltage visit. Now it is our RL. So this low RL can be a battery which you want to charge. It can be some LED, etc. Some load is there. Now current is coming from the source. So let me call it IS, and current may, if the diode is active or current is flowing through the diode, you can think some IZ current is passing through the diode. For that case, the diode have to be breakdown, or we say the voltage across the diode is more than the breakdown voltage or VZ, and this is the current passing through the RL is. So we're going to analyze the circuit. For what are the cases possible? First, we're going to consider that in the circuit, the Vs is such, the Vs value of Vs, Rs, RL is such that the Zener breakdown occur. That means the voltage across the Zener diode is more than the Vz and current is flowing through the voltage. So case 1. So here it's a electronic term. So we call Zener breakdown occur. So in this case, for how this circuit looks like. So it's the circuit going to become a very simple circuit, and it is the most easiest case. So in this case, what going to happen? The Zener diode of voltage Vz will become a battery. You can think like that, a battery of voltage Vz. So this is the case. So we already in the IV characteristic we see that when the voltage across the Zener is Vz, it start conducting and voltage remain pretty much constant. Also in forward bias, voltage across diode remains 0.7. So that is basically our coming from the barrier potential in the depletion region. So here also the voltage, when the breakdown occur, voltage around the Zener diode will be constant, which is the basically the Zener breakdown voltage of that particular diode. So therefore the equivalent circuit become so we have in the circuit, so we can neglect the other part. So now we have just a battery of voltage Vz. So this is RL, so this is IL. Therefore IL is Vz by RL, simply from the Ohm's law. So that's all. That's how we can get the current through the load. Now this is, we discussed the case 1 when Zener breakdown occurs. Now second case, so here no breakdown. It's also a easy case, nothing to worry about. So when a breakdown don't occur or a diode not start conducting, then the diode has infinite resistance, or we can think diode is actually not there. So here we replace the by diode by just a opening. So our equivalent circuit become Here is some Vs at source. This is Rs. This is RL. Now instead of Zener, since there is no breakdown occur, it's open. Now the current I will go through both the RS and RL, and since the resistor is in series, the same current will pass through that. Now the current in the circuit, which I am calling it at IS anyway. So IA is going to be simply Vs by Rs plus RL, as both the equivalent resistance in the circuit is Rs plus R. So this is the current through the circuit. Now question is how to know that Zener breakdown occur or not. So that's a good question. So condition for Zener breakdown. So this part we need to understand a little bit. The initial things we discussed was really easy, and if we just understand what is happening there, we don't need to remember any formula, at least in this case. But here it is better to remember the final result for condition for Zener breakdown. It will save a little bit of time, our time anyway. So the physics wise, so let me write down the physics. If so we will check it, like if the voltage across RL is more than Vz in the absence of Zener, then the breakdown will occur. So this is the physics. So in our circuit, so this is Rs, so this is RL. Now there is no diode. Now if the voltage across the load become more than the Vz in the absence of this diode, then we can certainly say that a Zener breakdown will occur. So let me check. So let me write down first what is the current passing through the circuit, that we already see in the previous case when there is no Zener diode or no breakdown occurring. So current through the circuit, let me call it Is, is obviously Vs by RL plus Rs. So I am applying Ohm's law, which is Vs equal to, again, so I am discussing it, IR. Now this is the current through both the load and both the resistance. Now the voltage drop across the load resistance, which is VL, is given by current through the load, which is basically in this case Is, into the load resistance. So we can write, so this is RL by RL plus Rs into Vs. So this is a dimensionless part, and this VL, voltage across load, becoming the ratios of resistance kind of a thing into Vs. Now if this VL is greater than Vz, breakdown occurs. So in some cases, our first some problem, or some cases our first problem, or our first goal will be to check is Zener breakdown is occurring or not. If the breakdown is occurring, then immediately we will move to this formula, case 1, and we can very easily calculate IL. If Zener breakdown is not occurring, then we can move to this case 2, or this formula, to calculate the current through the entire circuit, or current through the both load as well as the RS. So okay, now This I already, one thing I forget to mention, that RS is a series resistance. Obviously, it's a series resistance, and it's basically protective resistance. RS actually protect the Zener diode. So question is how it is protecting the Zener diode, that we are going to discuss. So Zener diode, if you going to buy in a going to buy a Zener diode in a market, so they will usually ask two things. Uh, what is the Zener breakdown voltage of the Zener diode? So let's say you can say 6 volt, but immediately they will ask what is the power of the Zener diode. So in the market we can get 1 watt Zener diode, quarter watt, half watt, even if 2 to up to 5 watts of Zener diode we can get in the market. So then the larger the watt, the general size will be bigger and bigger. So they will give you a basically a bigger and bigger cylinder. You can think like that. Okay. So that means we know one thing, that is the power of the Zener diode. So this is also a known thing. So obviously power of the Zener diode is given by nothing but Zener breakdown voltage. So that is the voltage, that is the maximum voltage you can think across the Zener diode. Whatever the voltage you supply after Vz, when the voltage is more than the breakdown voltage across the Zener diode remain Vz into Iz max. So this is the maximum current we can safely pass through the Zener diode. If that current exists, then the Zener diode will be destroyed. And you can see little bit of burning smoke fire in your circuit. Anyway, so the purpose of this RS is actually maintain this IZ. So this is the part. So now we have one, then let me calculate then scenario where Zener breakdown occur, and what should be the minimum value of RS. If the Zener breakdown doesn't occur, then there is no meaning of this RS. Current will pass through RS and RL. It will do it not going to disturb the Zener diode, or current will not pass through. Anyway, so minimum value of RS in the circuit, so that we can protect the Zener. So let me draw the circuit again. So why I am drawing, you will get it. So this time lots of current will be there. So this is Is, which is coming from the battery, or you can say coming from our rectifier circuit. This is RS, this is the Zener diode, this is the RS. Now after passing, this is a node in the circuit. So here will be the branching of current. One current is Iz, and this will be IL. So if we apply KCL at this point N1, KCL at N1, immediately give me Is is equal to Iz plus I. Now here remember the case. Zener breakdown already occurred. So better to replace now this diode as a battery of voltage Vz. Otherwise, the current will not pass through the Zener diode. So it is very easy to get the IL now. IL is Vz by R. Anyway, now we know the power of the Zener diode. Vz Iz max. So Iz max, or you can think, yes, so in this case we will say the diode is such that it is just allowing the maximum current or just barely protecting the generator. So Iz going to be um, Vz by Vz. So that is somehow known to us. Now actually the purpose of this circuit is that when there is no load, again when there is no load, it should allow the Iz current through the circuit. So actually when there is no load, but anyway we can think like that, or also like the way we are doing also we can do that also. So let me remove this. Okay, so now it's very easy to calculate the RS. So we can apply a KVL here in this circuit, and KVL in this loop, in loop L1, is give me Vs, sorry my bad, so I'm going in that direction, so it will be Is Rs. So I am going in the direction of electric field plus Vz. Here I am going in the opposite direction of electric field. It will be Vz. I am going in the direction of electric field, it is Vs and equal to 0. Now the value of Ra is going to be Vs minus Vz. So that is the maximum load voltage, sorry, maximum source voltage we can have, Vz minus Vz by Is. So what is the maximum Is? So Is max, that you can, the value of Is we can put at least, so we want to protect our diode when Iz max is flowing through the circuit, and we, you can think temporarily there is no RL. So the current, if there is no RL, no RL, your Is have to be Iz max. Therefore Rs will be equal to Vs by Vz. So this Iz max we already know, that is power of the Zener diode by Vz. So this formula give us a idea that how to choose the minimum value of Rs such that we can protect the Zener diode. So now we will do some sums to understand what is happening or not. So let us first check this problem. So here Zener diode with 5 volt Zener voltage is used to regulate an unregulated DC voltage of input 20 volt. For a 400 ohm resistor connected in series, the Zener current is found to be 4 times the load current. Now they want to know the load current IL and load resistance R. So they given in the question. So let me draw better the circuit for our understanding. So okay, so they given Vz is 5 volt, Rs is 400 ohm, Vs as 25 volt, and they want to know IL and R. So this is Vs 25 volt, this is Rs 400 ohm, this is 5 volt. Now RL is there. IL is also there. Now by just looking on the number, I can surely say that Zener breakdown is occurring because this Vs is very larger than Vz, that Vz 5 volt. But anyway, we can check first that is breakdown is occurring or not. This is one case. If breakdown is occurring, that's good. Okay, so let me check the problem once again. If they give us something, so the Zener current is found to be 4 times the load current. So Iz is basically 4 times of IL. So that is given. So they given Zener Iz is equal to 4 times of load current. So this, then it is sure, obviously it is given in the question, then Zener breakdown occur. So then it is very easy to calculate. Okay, it's not that. So anyway, it's basically then I can simply write down IL load current is basically, so as the Zener breakdown is occurring, it is Vz by RL. So it is coming into our case 1 where Zener diode is acting like a battery of Vz, battery of voltage Vz. So this is, now we have one equation, but we don't know, the value of RL, neither RL neither IL. So we also, they have given some other things. So here it is Iz, here it is IL, and this is Is. So we can write down from the KCL, Is is Iz plus IL, and we know Iz is actually 4 times of IL. That you can use. This is one information we can use. So better to write Iz plus IL is Iz by 4. So it is 5 Iz by 4 kind of a thing. So this is the Is now become this. So this is one way I am looking into this problem. So now I have Is. Now if I apply just a simple KVL here, so it can very easily get the value of Iz to me. So KVL, so here we apply KCL at node N1, and here we are applying KVL at loop L1. So ISRS plus VZ minus VS is 0. So IS is 5 IZ by 4 into RS, and VS is 25, VZ is 5, it is this side is become 20, RS is 400, so it is 5, so IZ is 1 by 25 ampere. Therefore, IL is 4 times of that, sorry, IL is 1 by 4th of that. That means IL is 4 into 25 is equal to 1 by 100 ampere, and we can convert it to milliampere, it will be 10 milliampere. And the RL, the load resistance, I can use this formula, RL is VZ by IL. VZ hour is 5, this is 1 by 100, 500 ohm. So let's check the option, am I right or wrong? So there are 500 ohm, 10 milliamp. Now move to the next question. In the following circuit, the reading of the ammeter will be. So they want to know in this circuit IL. Okay. So in the problem 2, they given Vs equal to 12 volt, Vz equal to 4 volt, RL equal to 400 ohm, and RS equal to 100 ohm, and they want to know the IL. Okay, back to the board. So let me draw the circuit again for just our understanding, or okay, let me draw it just. RS is 100 ohm, so 12 volt, this is Vz, this is RL 400 ohm, and there is some ammeter, and that will indicate the IL. So first check the Zener breakdown occurring or not. If the Zener breakdown is occurring, then life going to be very easy. Here almost everything is given. So if there is no Zener diode, so let me call this voltage as V test, which is the voltage across the load when there is no Zener diode, which is RL by RL plus RS into Vs. Let me calculate it first. And if this V test going to Vz, then obviously the Zener breakdown going to happen. So RL is 400 ohm. Then in the denominator 400 plus 100 going to be 500 ohm into Vs is 12. And let's see. How much we are getting. Is it more than 4 or not? It is obviously more than 4. So let me calculate. I am doing it very approximately. It is going to be 2 point something, 2.4 or something. So it's obviously 8 point something, and which is more than the visit. So it is obviously that breakdown occur. Breakdown occur. So therefore IL load current will be nothing but, so here now the BZ act as a battery, and that battery will control current through the load, and this is the purpose obvious, that I always want the voltage across my load remain constant. So VZ by RL 5 and the load voltage was 400. So this is going to be the current. So it's 1 by 80. So I have to check. So better if I convert it to milliampere, 1 by 80 into 1000. So it is around 12.5 milliamp. Let's check, is there option on. So we got 24 milliampere, 10 milliampere. So it seems like I made some calculation error somewhere. Okay, I understood where I made the mistake. So Zener breakdown voltage is not 5, it is 4 volt. So now it will be like 1 by 100. 1 by 100. So that makes our life easy, obviously. Just now it's a 10 milliampere. Okay, let me go back to the board again to check. So I made the mistake. Yeah. So VZ is not 5, VZ is 4, and rest was really easy. So now the last question in this series. The Zener diode has a Zener voltage of 10 volt. Maximum power dissipation of 0.5 watt. So that means it's a half watt Zener. The minimum resistance to be used in the series with the diode for the safety when it's connected to a 25 volt power supply. So Vs is 25 volt. So we already discussed that when the sudden somehow load is disconnected, then the current has nowhere to go. So it will pass through the RS and pass through the generator. If the current through the Zener diode exists, the allowed current through it, which is controlled by its maximum power, then the Zener will be destroyed. So here the idea is very simple. Power is given, both the voltage is given. So our goal is to calculate the RS. So in this case, we will consider there is no load, obviously. So this is the minimum case. If load is there, then obviously the value of RS will be little bit lesser, but it's a safety case. So okay, go back to the board. So these are the things is given. So I am just drawing the circuit again. So here is Vs, here is RS, and here is Zener. So our Zener breakdown occur. Actually, okay, our breakdown is occur. So we can replace the Zener as using a battery just for now. Visit, which is 10 volt. This is 25 volt. So also its power is half watt Zener. So VZ is VZ IZ max. VZ is 10 Iz max I want to find. I know only one thing, the power is half watt. So Iz max is becoming 1 by 20 ampere. Sorry, 1 by 20 ampere. So we got our Iz anyway. Now uh, again a simple KVL can solve our problem. This is our L1. We already discussed. I can like blindly write it down now. Now in the circuit, we will consider that Iz max is only flowing. So let me check it again. Yeah. So Iz max Rs plus Vz minus Vs is 0. So Rs is Vs minus Vz by Iz max. So anyway, someone can remember this formula directly. It's a easy formula. Just voltage by current. Actually, difference of voltage by current. So Vs is 25. So let me check it again. I don't want to make a mistake like before. Then by 10, and Iz max I got 1 by 20. So this 15 by 20. So this 15 into 20 ohm. So 300 ohm. So this is going to be the value of Rs in the, at least this should be the minimum value of Rs. So let me check the answer here. So these are the three types of question we usually going to face in Zener diode. So thank you. Let's end this class.